KSP problems type 3, type 3B. So this is a review of the type 3 problems. So that is a good opportunity to work with that. We're also going to see a common ion effect, a review of type 2B. And as far as this 3B problem, it's not all that common, but I think it's a good review of component parts. And for a higher level question, you get a chance to look at that too. So let's take a look here. Will a precipitate form? Find the concentration of these ions. So a solution is prepared by mixing 0.500 liters of 0.400 molar barium nitrate with 0.300 liters of 0.200 molar potassium sulfate. That's a precipitate form. So right away, I'm given amounts of two things, and right away I'm thinking, hey, this looks like it's a Q or QSP problem, and then I'm going to try to, I guess we call it QSP instead of trial KSP. But what we're going to be trying to do is figure out a precipitate forms first. So that's a good review of a type 3 problem. Let's take a look. We're going to be talking about barium sulfate forming. Okay, the other possibility would be potassium nitrate, but an alkali metal and a nitrate are both very soluble. So that's going to have a very high solubility. Barium sulfate's not, and you're given the KSP for that. So let's just focus on that. And I'm going to take the equation, the dissociation equation for barium sulfate being dissolved in water, which would be Ba+2 and SO4 -2. We know with this low KSP that doesn't happen to much of an extent, but we don't have very large concentrations. So let's see if that's going to happen here. All right, my KSP expression is Ba+2 and SO4 -2 concentration. And what I do to figure out my concentration of barium is I take the liters in molarity. Okay, that would give me moles, but I have to divide that by the total liters. And I think the easiest way to do this is with the dilution factor. Notice you have 0.400 molar barium nitrate. You have 0.5 liters of that, but you have 0.3 liters of something else. So essentially 5/8 or 0.5 out of 0.8 of these liters are from the barium source. So I take that 0.4 times 0.5 over 0.8, which equals 0.250 molar. Okay, notice the barium is, there's one barium. There's not a 2 there, like where you'd have to double it. There's just one barium. So that's how you'd do that right there. This is very much like what we did in the lab during Unit 12 or Chapter 12 when we had that big table with kinetics. Okay, we did some things with dilution factors. The other example is, again, 0.3 liters of 0.2 molar potassium sulfate. Again, the sulfate is in a 1-to-1 ratio with the potassium sulfate, but you have 0.200 molars, but only 3/8 or 0.3 out of the total 0.8 liters is from the potassium sulfate. So I take that molarity of the sulfate and then I times it by 0.3 over 0.8 and I get 0.0750 molar for the sulfate. So I get my concentration of barium, get my concentration of sulfate. I have to work a little harder to do that because it was a mixture of these two solutions. I plug that into the KSP, which would also be the QSP expression, and I get 0.0188, which is clearly larger than 1.5 times 10 to the negative 9. Okay, so this would say, yes, you are going to get a precipitate in this case. Because Q is larger than K, the products are going to combine together to form more reactants in this way, making the solid BaSO4. Now, the other question is, even though that's true, there's still going to be a little bit of these ions floating around. So how much of these ions would be floating around? And this gets more complex, this question, as we do that. So let's take a look at that other piece. That first type of question is really common, doing the Q thing. This one's not quite as common, but let's take a look at it. It does come up from time to time and see if we can challenge ourselves to do that. Okay, so what I'm going to do is look at my molarity of barium and sulfate. I'm going to actually think of this almost like an excess limiting reactant problem where I have 0.250 of barium and I have 0.0750 of sulfate. And these are going to combine 1 for 1 until something's gone. Okay, so I think about this, and essentially all the sulfate's going to react because they're in a 1-to-1 ratio. I have less of it. Okay, and that's going to leave me with 0.175 molar barium left and nothing of the sulfate. Now we know that there is going to end up some sulfate in the solution because it is an equilibrium system. So even though all this might react to form barium sulfate and keep it in the solid state, it is going to reverse back to a slight extent. So I don't think you have to draw the ice box to show this, but I did. I kind of went back, and now I'm turning this back into a type 2b problem or common ion effect problem, where I know the barium concentration is this 0.175. I know I have zero sulfate, but we know it does go back to some extent. And the barium sulfate, I don't record that because it's a solid. We don't really care how much is in there. Okay, it's not going to affect things. So what happens is this is a small amount. How small is it? That's what X is. Well, these are going to react in a 1-to-1 ratio. So this will be 0 plus X is X, and this will be 0.175 plus X is 0.175 plus X. So just like in the other common ion effect type 2b problem, the X is going to probably be really insignificant, so we don't have to worry about it in our math. So now we can just take the KSP equals barium plus 2 and SO4 minus 2 and plug things in. We know that KSP is 1.5 times 10 to the negative 9th. We use the common ion effect, essentially this 0.175. We ignore the plus X, and then we know that the sulfate is the X, and we end up solving for X, which is a sulfate, which is really, really, really small, 8.6 times 10 to the negative 9th. So in other words, if I try to take this and dissolve this in barium sulfate, and I have a lot of barium already there, then there's going to be less of this. So it's going to be unbalanced. It's not going to be equal amounts because I already had a lot of barium right there. But what would my answers be? I already figured out the 0.175 molar. Technically, it's 0.175 plus X, but adding 8.0000000086 to this is not going to make a difference. And then this would be my concentration of SO4 minus 2. So reviewing back to this problem, the problem you're going to get most often is just a Q type of problem, a regular 3 problem, type 3 problem, or type 3A, I guess I can call it. Notice it's a little fancy work to get the right molarities for this, but on occasion you could be asked to go deeper, and this is what you would need to do to figure out the Ba plus 2 and then the SO4 minus 2 concentration right here. Thanks for watching. There's another one here to try in the homework packet for you to try. Thanks.